In episode 77, titled Requirements Analysis, Business, Technical, Compliance, and SOW Inputs, the focus is on analysis as the disciplined act of turning messy inputs into clear constraints and measurable success tests. Architecture work fails more often from misunderstood requirements than from misunderstood technology, and the exam likes this topic because it tests whether you can translate vague objectives into concrete decisions. Requirements analysis is not a meeting. It is a process that produces artifacts people can agree on, implement against, and audit later. The inputs usually come from business goals, technical realities, compliance obligations, and the statement of work, and each input category can push the design in different directions. Your job is to normalize those inputs into a set of constraints and acceptance checks that define what done and correct means. When you do that well, you reduce scope creep, prevent redesigns late in the project, and avoid unpleasant surprises during audits or cutovers. The exam rewards this mindset because it is how real projects succeed. Clear requirements, explicit assumptions, ranked priorities, and verifiable outcomes. This episode builds a practical way to gather, reconcile, and document those inputs so the final design is defensible. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Business inputs describe goals, risk tolerance, and stakeholder priorities, and they define why the project exists and what outcomes matter most to leadership. Goals might include improving uptime, reducing cost, enabling expansion, meeting a customer demand, or supporting a new product launch. And each goal implies different architectural trade-offs. Risk tolerance tells you how much disruption is acceptable and what level of resilience and security investment is expected, because not every business can or should pursue the same level of availability or control. Stakeholder priorities matter because different groups value different outcomes, such as security teams prioritizing visibility and control, while operations teams prioritize simplicity and maintainability. Business inputs also define what failure looks like, whether that is revenue loss, safety impact, reputational harm, or regulatory exposure, and that definition shapes how strict requirements must be. The exam often tests whether you can separate business wants from business needs, and whether you can translate them into measurable constraints like downtime budgets, recovery objectives, and performance expectations. Business inputs also include the user experience dimension, such as acceptable latency for applications or acceptable friction for authentication. When you capture business inputs clearly, you anchor every technical decision to an agreed purpose rather than to personal preference. Technical inputs describe the existing architecture, dependencies, and skill limits, and they determine what is feasible within the current environment and timeframe. Existing architecture includes what networks, platforms, and identity systems are already in place, because designs that reuse stable foundations are often lower risk than designs that replace everything at once. Dependencies include upstream services like domain name system, identity providers, monitoring platforms, and existing connectivity models, because these constraints determine what can be changed safely and what cannot. Skill limits are an often ignored input category, but they matter because a design that requires expertise the team does not have will fail in operation even if it works in a lab. Technical inputs also include operational constraints like maintenance windows, change control processes, and the availability of automation tooling, because these influence how safely you can deploy and maintain the solution. The exam tests this indirectly by presenting designs that are technically correct but operationally unrealistic for the described team, and expecting you to choose the design that fits the environment. Technical inputs also include integration constraints, such as legacy systems that cannot be modified easily or network segments that cannot be renumbered due to dependencies. When you document technical realities, you protect the project from designs that are elegant on paper but brittle in production. Compliance inputs describe regulatory controls and audit evidence needs, and they define non-negotiable requirements that must be met regardless of convenience. Compliance can include data residency rules, encryption requirements, access control mandates, logging and retention obligations, and segregation of duties requirements that influence how systems are administered. Evidence needs are especially important because compliance is not only about doing the right thing, but also about proving it, meaning you must plan for logs, reports, access reviews, and documented procedures. The exam often tests compliance as a forcing function that changes architecture choices, such as requiring private connectivity for sensitive data flows, requiring stronger authentication for administrative access, or requiring detailed audit logs for privileged actions. Compliance also affects vendor selection and service configuration, because not every service supports the same logging granularity or retention behavior. These inputs may also include internal policies that are stricter than external regulations, and those internal policies often have real enforcement consequences. When you treat compliance as an input category with explicit controls and evidence outputs, you avoid surprises during audits. Compliance requirements should therefore be expressed as specific control statements and proof artifacts, not as vague must-be compliant language. Statement of work inputs describe deliverables, timelines, and acceptance criteria, and they define the boundaries of what is being delivered and how success will be judged contractually. Deliverables specify what artifacts will exist at the end, such as designs, configurations, documentation, training, or migration support, and they should be explicit so there is no ambiguity. Timelines define when milestones must be met, which influences design scope because complex architectures may not be feasible under aggressive schedules without increased risk. Acceptance criteria define what tests must pass and what evidence must be provided for the work to be considered complete, which pushes you to define measurable outcomes early. The exam tests this because projects fail when teams build something technically impressive that does not match the statement of work's defined scope and acceptance tests. Statement of work inputs also clarify roles, such as who supplies circuits, who approves changes, and who signs off on cutover, which affects operational readiness. They also define change control expectations and support windows, which influence migration planning. When you capture statement of work inputs clearly, you align the technical solution with contractual reality and reduce disputes at the end of the project. Capturing assumptions explicitly is essential when information is incomplete, because missing details are normal and hidden assumptions are a major source of failure. An assumption is a statement you believe is true for the purpose of design, such as assuming a certain number of users, assuming a certain bandwidth availability, or assuming that an identity provider supports a required authentication method. Making assumptions explicit creates a clear checkpoint for validation, because stakeholders can confirm or correct them before the design is implemented. It also protects the project, because if an assumption proves false, you can show that the design was based on agreed information and that changes are needed. The exam often tests this by presenting ambiguous scenarios and expecting you to state what must be clarified or assumed before finalizing architecture. Assumptions should be written as testable statements with an owner and a validation plan, not as vague guesses. This also ties into risk management because assumptions represent uncertainty, and uncertainty must be managed explicitly. When you capture assumptions openly, you reduce the chance of building the wrong solution due to silent misinterpretation. Conflicts are inevitable because business, technical, compliance, and statement of work inputs often push in different directions, and the resolution method is to rank priorities and document trade-offs. Ranking priorities means deciding what is most important when you cannot satisfy everything fully, such as choosing between cost reduction and high availability, or between rapid delivery and deep security controls. Documenting trade-offs means writing down what you chose, what you did not choose, and why, including the risk accepted and the mitigation planned. This is not political theater, because trade-offs become the justification when problems arise later, and they also guide future improvements when constraints loosen. The exam tests whether you can identify conflicting requirements and choose a defensible path rather than pretending every goal can be achieved simultaneously. Conflict resolution also involves stakeholder alignment because different stakeholders must accept the trade-off, especially when risk is being accepted or budget is being consumed. Good trade-off documentation is concrete, linking the decision to specific requirements and impacts rather than to generic statements. When you rank and document, you convert conflict into a managed decision rather than a hidden time bomb. A scenario where compliance forces private connectivity and stronger logging is a classic example of compliance inputs shaping architecture choices beyond what business and technical teams might choose by default. If regulated data must not traverse public networks, private connectivity patterns become required, even if public endpoints with firewalls would be cheaper or easier. If audit requirements demand traceability of administrative actions, logging must be stronger, more centralized, and more tamper-resistant, even if the team would prefer minimal logging for simplicity. Compliance may also require multi-factor authentication for privileged access and detailed retention policies for logs, forcing choices about identity integration and log storage. The exam uses scenarios like this to test whether you can recognize compliance as a non-negotiable constraint and adjust the design accordingly. This scenario also shows how the success tests change, because you must validate not only that the system works, but also that the required evidence exists. Private connectivity and logging are architectural features, but they are also compliance evidence producers, which is why they must be planned from the start. When you see compliance language, you should expect connectivity and logging requirements to become stricter and more explicit. Skipping stakeholder alignment is a common pitfall because it leads teams to build the wrong solution, even if the solution is technically correct for a different understanding of the problem. Stakeholder alignment means confirming that business owners, security owners, operations owners, and delivery owners agree on goals, constraints, and what success looks like. Without alignment, the project may optimize for the wrong metric, such as building a high-performance design when the real priority was auditability, or building a secure design that is too complex for the operations team to maintain. Misalignment also creates late-stage scope changes because stakeholders discover missing requirements after design decisions are already embedded. The exam tests this pitfall by presenting projects that meet some requirements but fail the real stakeholder need and expecting you to recognize the need for upfront alignment. Alignment also includes communication about trade-offs because stakeholders must accept the risk that remains. When alignment is skipped, the project often ends in rework, delays, and frustration because the solution does not match the original intent. Requirements analysis therefore includes not just collecting inputs, but also confirming shared understanding. Ignoring operational ownership is another pitfall because designs fail at handoff when no one is prepared or empowered to operate what was built. Operational ownership means identifying who will monitor the system, patch it, respond to incidents, manage credentials, and approve changes after go-live. If ownership is unclear, incidents linger because responders do not know who is responsible, and changes are avoided because no one wants to take risk on an unfamiliar system. Operational ownership also includes training and documentation requirements because the team must understand the system well enough to keep it stable. The exam tests this by describing projects that deploy successfully but then fail in production due to lack of ongoing management and expecting you to include ownership and handoff planning as part of requirements. Ownership also influences design choice because a simpler design may be preferable if the operations team is small, even if a more complex design is technically superior. Requirements analysis must therefore include an operating model, not just technical specs. When ownership is explicit, designs are more likely to remain healthy over time. Quick wins include using a consistent template and reviewing it with stakeholders, because structure reduces missed inputs and stakeholder review catches misinterpretations early. A template forces you to capture business goals, technical constraints, compliance obligations, and statement of work deliverables in a repeatable format, making it easier to compare projects and to ensure completeness. Stakeholder review turns the template into a shared artifact, allowing each group to confirm that its needs are reflected and to flag conflicts before implementation begins. Reviews also help validate assumptions and clarify acceptance criteria, reducing ambiguity and preventing late-stage disputes. The exam often rewards this because it demonstrates process maturity and reduces risk across complex projects. A consistent template also supports traceability because each design decision can be linked back to a requirement entry, which is useful for audits and post-incident reviews. The real benefit is that templates and reviews prevent the most common failure mode, which is building something that no one asked for in exactly that form. When you treat requirements as an artifact, not as a conversation, success becomes more repeatable. A useful memory anchor is business, technical, compliance, SOW, assumptions, because it captures the 5 buckets that must be filled before architecture decisions are finalized. Business defines the why and the risk tolerance. Technical defines what exists and what is feasible. Compliance defines non-negotiable controls and evidence needs. Statement of work defines scope and acceptance, and assumptions define what you are treating as true until validated. This anchor is useful on the exam because it helps you interpret scenario questions that provide only partial information, prompting you to identify what inputs are missing or what assumptions must be stated. It also helps you organize a requirements summary quickly because you can categorize each statement into one of the buckets and see where gaps exist. When you can use this anchor to extract and structure inputs, you demonstrate a methodical approach rather than ad hoc reasoning. It also supports conflict resolution because you can see which bucket is driving a particular constraint and whether it is negotiable. When you apply the anchor, requirements analysis becomes a disciplined inventory rather than an informal discussion. To practice extraction, imagine being given a narrated project description and being asked to pull out the key inputs, and you would start by sorting statements into the input buckets. Business inputs would include the project goal, such as improving uptime or enabling a new service, and any stated risk tolerance or priority, such as cost control or customer experience. Technical inputs would include existing network architecture, identity systems, connectivity constraints, and team skill limits that influence what can be deployed. Compliance inputs would include any mention of regulated data, required logging retention, encryption mandates, or audit evidence requirements. Statement of work inputs would include deliverables, timeline milestones, and acceptance tests, such as performance targets or failover tests that must pass. Assumptions would include any unstated but necessary parameters, such as expected user counts, traffic volumes, and operational ownership assignments, which you would flag explicitly for validation. The exam expects you to do this extraction quickly and accurately because many questions are essentially short requirement analysis exercises. When you can extract and categorize inputs, you can then propose architecture choices that match the constraints. This is how you connect narrative descriptions to technical design. To close episode 77, titled Requirements Analysis, Business, Technical, Compliance, and SOW Inputs, the essential process is to collect inputs, translate them into constraints and success tests, state assumptions explicitly, and resolve conflicts by ranking priorities and documenting trade-offs. Business inputs define goals and risk tolerance. Technical inputs define existing architecture, dependencies, and skill limits. Compliance inputs define required controls and evidence. And statement of work inputs define deliverables, timelines, and acceptance criteria. Assumptions must be written down when information is incomplete, because hidden assumptions are a common cause of wrong solutions and late-stage rework. Scenarios where compliance forces private connectivity and stronger logging illustrate how constraints change architecture and also change what must be proven at acceptance. The major failure modes are skipping stakeholder alignment and ignoring operational ownership, both of which lead to solutions that cannot be sustained after handoff. Quick wins like a consistent template and stakeholder review reduce omissions and surface trade-offs early. The memory anchor of business, technical, compliance, statement of work, and assumptions provides a reliable checklist for completeness. Your rehearsal assignment is a requirement summary rehearsal, where you take one project description and write a short, structured summary in those 5 buckets, because that rehearsal is how you build the analysis habit the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.